This video covers Lesson 5-3 for Secondary 1 Math, Scatter Plots. Okay, so Lesson 5-3, Scatter Plots. So in previous lessons, the relationships we've explored have been linear. Today we will be exploring relationships that are exponential. So remember, exponentials, we can't use a ruler and draw a straight line for our line of best fit, but instead we have a curve. So what we're going to do is we're going to jump over to our Desmos.com calculator, and we're going to follow steps 1, 2, and 3 here in the notes to enter our information and create a graph and eventually find the equation for the line or the curve of best fit, since we're going to be dealing with an exponential situation. So here we are at our Desmos.com calculator, and the first thing we're going to do is create a table. So we're going to go over to the plus sign, click it, go down to table. And that opens up this table. And what we're going to do is we're going to enter this information from the table in the warm-up. So the first one is 3. If we go down, the next one's 14. Then we got 21, then 24. And we're going to continue to enter that information. Then you're going to go over to the Y column and enter the other information. So 487. Then you're going to go to 791. Okay, and continue to fill this whole table out. Once you have the table out, you're going to hit play for this video. But right now, go ahead and pause it and enter the information into your table. Awesome. Now that we have all of the data into our table here on the left, it's plotted it here in our graph, but we still don't see it. So we're going to go up to the wrench here in the top right. We're going to click on this, and we're going to change our parameters. So our x-min and our x-max. So looking at our table, the minimum value would be 3. So I'm going to go a little less than that. So I'm going to go down to 0. The highest x value is 46. And so I'm going to go a little above, maybe 50. Then we come down here to our y values. We're going to do the same thing. The lowest y value is 487. So maybe 450 would be a good fit there. And then we can come up and go up to our highest, which would be, let's see, about maybe 10,000. And so we can see here, if I click off of it, here's our graph. Now it made it square, so we don't quite see everything. So I can click this minus sign here. You can see a little bit better. But we're starting out low, and we're slowly growing. And you can see what's happening here. So again, we see that same kind of curve. And that curve would look a little differently if I were to try to fit it into that same parameters that were on the graph that we had in our notes. But you can still see the curve happening here. So we still have an exponential. Okay. Then to find our curve of best fit, or the equation for the curve of best fit, we're going to click here on number 2. And we're going to type in, we're going to go y1, we're typing in, equals a, and then we go b, and then here we're going to go ahead and we're going to put a caret symbol to make it go to exponent. Okay, that's the Shift 6 key on your computer. And then you're going to go ahead and go X, and then a little 1 to hit sub 1. Then I'm going to hit, I made a mistake here. I put the equals, which is a common thing. We actually want to put in the, oh, goodness. There we go. We want to put in the similarity sign, because then it creates our line of best fit for our data. And you can see how that curve fits all of this data really well. And then it gives us this information, okay, that's going to help us. Now, remember, you have to click in that log mode. If you don't, you're not going to get the R, so make sure you get that in there. And here's our data for our curve of best fit equation. So using the Desmos.com calculator, as well as the warm-up, we already decided that this situation was not linear. And so we're going to say that it is exponential. And the reason that we decided this was exponential is because it didn't fit a straight line. And now be careful, because the points are going to be a little bit off that line, even if we drew a straight line and it was a linear relationship. Here, they fit a nice curve, and so that's why we're saying this is exponential. So then we had to come up with this equation for this curve of best fit. And we gathered this data over here on the right from our Desmos.com calculator to help us in writing the equation. So this is the general form. That's how we're going to write it. So we're going to start out y equals. And then we're going to start with our a. And our a value is 315.446. And we're going to round this to the nearest, we're going to round to the nearest whole. And so our nearest whole would be 315. Next, we're going to multiply that by b. And b is right over here. We're going to round this to the nearest thousandth. So remember, we got tenths, hundredths, thousandths. So it's 3 decimal places. So we're going to look at the 6 right here at the end. And that tells us to round up. So we're going to put 1.078. That's rounded to the nearest thousandth and raise it to the xth power. And there's the equation for the curve of best fit. Next, number 2 says, what is the R coefficient? Well, the R coefficient is right here. And we're going to round this to the nearest hundredth. That's 2 decimal places. So here, that we're going to round it to the 8th spot. So we got to look next to that. That's a 7. 7 rounds up, so we're going to have 0.99. Okay, is our R coefficient, or 99 hundredths. So what is the correlation? Well, how would we describe this correlation is really what we're asking here. And we would say that this is a strong correlation because it's so close to 1. And it's positive because it's a positive value, right? It's a positive 0.99. So strong, positive. Number 4, write a sentence explaining what the initial value, or A, represents. Well, A is 350. We can see that right up here. So we know that value, but remember our initial value is always our starting. And so it has something to do with the 0, 315, that would be our point. But if we refer back to the information on that warm-up, like the top of the table, it's talking about the actual years since 1960. And because it's talking about years since 1960, we got to say in 1960. So that's how we're going to start here. In 1960, there are and then we would say 315, because that's our y value, pairs, because this is what it represents, pairs of bald eagles. So in 1960, I should have said were 315 pairs of bald eagles. Okay, number 5, write a sentence explaining what the growth factor B represents. Well, our growth factor is 1.078. So remember, when we break this up, we could write this as 1 plus 0.078. And that 0.078 is how much we're growing, right? The 1 helps us just stay the same. So what we're going to say is that on average, remember, because it's not going through every point, on average, the number of pairs of bald eagles grows 7.8%. So notice I changed it to a percentage here. 7.8% every year. Okay, so this next page, we're going to talk about a different situation. So this table shows the population of Utah since 1900. Okay, so we're going to follow the same steps, and we're going to enter the information into our Desmos calculator. And then we're going to figure out, is this linear or exponential? Make sure you understand why we're deciding this. And then we're going to answer these other questions as well by writing the equation and getting the information from our Desmos calculator. Okay, so we're back at our Desmos.com calculator, and you'll notice I don't have anything on the left side anymore. I just deleted it. All you have to do is go up here and click this X button. It takes care of that frame. So what I do need to do now is open up a new table. So here's my table, and I'm going to go ahead and start putting in the information in under X for the years since 1900. So 0, we got enter, then you hit 10, and you'll notice it's seeing a pattern. So if I want to follow this pattern, which we will in this table, I can just continue to hit enter till I get to the bottom. Under the Y values, we're going to have the Utah population in thousands. So the first one was 277, the next was 373, and then I'm going to continue to fill it in. So go ahead, pause the video, enter the information into your table, and then hit play. So pause the video now. Okay, so now that we have the information in our table and it's plotted here, I'm going to create a different window so it shows the information better. So I'm going to go up to the wrench, I'm going to click, I'm going to come over here, I'm going to change my X min, I'm just going to make it 0. You can barely see the point there, so maybe I should make it a -5 just to help me see the points. Then I'm going to go to my max, and that's got to be greater than 110, so I'll do 115. Okay, that way I have all my points on there. Then I'm going to go over here to my y-axis, and I notice that the smallest one is 277, so I'm going to go 200, and the highest is going to be 2,776, so I'll go 2,800, and there's a better window for what I want to see. And you can see that Desmos.com is making this a little different, but it's allowing us to see all the information, okay? And you can see this nice curve for this data, and that's what's helping us identify that this should be an exponential. Because as long as we're looking at a graph that is square, we can tell really well if it is an exponential equation or not for the line of best fit or curve of best fit. So what I'm going to do over here is I'm going to click in number 2, and we're going to type in our equation for an exponential. So we're going to go y. Now remember here we got to go shift and right above the tab to get this squiggly. Oh, my apologies. We got to hit y1. Then we're going to do the squiggly. Then we're going to go A and then B. And then we got to use the caret symbol, which is shift 6 on your keyboard. And then you're going to go X1. And there it is. And it's drawn our line of best fit. So as you scrolled up here, this information right here is going to, oh, and don't forget to click the log mode. We want the R, not R squared, but R. And that's going to tell us our correlation. Okay. So this is the information we're going to take and start writing our equation for the curve of best fit of this information. So again, like we saw with the Desmos calculator, we noticed that these points were following a curve versus a line. And so we're going to say that this is exponential. Okay, so this relationship is exponential. The other thing you can look for is if you're just looking at a table, it kind of gives you a little bit of an idea. But here we're changing by like 150, and up here we're changing, right? This one is changing by, what is that, about 200, okay? And I'm getting an approximation here. Down here is more like 100. So you can see it's kind of changing a little bit, but it might still be linear. But that graph really allows us to double check to make sure, yep, it totally is, or it isn't. Okay, and that's one way we can see. If you look down here at the very bottom though, these last 10, because each of these is changing by 10 for the x value, the last one is changing by like 500. And so that's a decent difference, so we can think that, oh yeah, maybe this is going to be more of a curve where it's growing and changing more and more each time. But that graph is really telling when we use that. Okay, so we decided that it was exponential because there was a nice curve to the data. The curve that we found for our curve of best fit on the graph looked really nice to it. And so we typed in this information on our Desmos calculator over here and got our correlation coefficient, our A, our B, so we can write the equation of that curve of best fit. So we're going to round the A to the nearest whole number. So looking at A, we have 275.8. So we're going to round that up. So we're going to say that this is y equals 276. Then we're going to go ahead and multiply it by B, which we're going to round to the nearest thousandth. Okay, so 10 hundredths thousand. So we're going to look at this 6 to decide if we need to round up or down or stay the same. And that 6 tells us to round up. So we're going to have 1.021 as our value of B. And we're going to raise that to the xth power. And there's the equation for the curve of best fit. Number 8, we want to decide what the R coefficient is. So we're going to again around to the nearest thousandth. So we're going over here to R. and that's going to be 0.995. And so 1 comes after that, because that's the 10 thousandths, and 1 doesn't round us up, so our coefficient is going to be 0.995. Now you might ask, hey, wait, why did we round to the thousandths here, where we rounded to the hundredths in the last one? Well, here, if we would have rounded to the hundredths, we would have ended up with 1. And it's not perfect. We saw that in our graph, that not all the points were on that nice curve. And so it's got to be a little bit off. So that's why we wanted to round to the nearest thousandths. So how do we describe this correlation? What is this correlation? Again, it's a strong correlation because it's so close to 1, and it's positive because it's a positive value. So we have a strong positive correlation. Number 10, write a sentence explaining what the initial value A represents. Now our initial value up here is 276. So 276, we got to think back to our table. So let's look back up at our table here. That would be population, so that's going to be people, thousands of people. So we have 276,000 people, right, living in Utah. And then if we go back up, that would be years since 1900, so that would be in the year 1900. So we could say, in the year 1900, the population of Utah was about 276,000. Now you might think, wait, why am I using this value instead of, sorry, this is a comma. Why am I using this value instead of the one in the table that tells me it's 277,000? Well, we're just basing this off of our equation instead of the actual numbers that we have, okay? So our equation can be a little bit off, but it's going to help us predict certain things moving forward. So number 11, we want to write a sentence explaining what the growth factor B represents. So just like last time, we're going to break this apart. And we're going to say, okay, this is 1 plus 0.021. And so that 0.021, we're going to change to a percentage, which would be 2.1, because we're moving the decimal place twice. So we can say that the Utah's population grows 2.1% per year on average. So adding that on average part helps us identify that, hey, this is not perfect, but it's going to give us a really good approximation of what the population was at different points in time. Number 12 and 13 have asked us to plot the data on the coordinate plane, label the x and y axis, and sketch a curve that best fits the data above. Now we did this with our calculator, but let's just get a little bit of practice here on this coordinate plane. So remember, we're going to label the axes, and the labels come from the title of each side of our table. So the x is going to be years since 1900. And the y-axis will be labeled as Utah's population in thousands. Now that we have the labels on our coordinate plane, or the graph, we're going to go ahead and plot the points. So the first one is 0, 277. So I'm going to go over to 0 and up to 277. So about here. Next one was 10, 373. So I go over to 10 on the x-axis and I go up to 373. Where, you do your best because it's not perfect. And then you're going to go ahead and plot the rest of the points and then draw your curve of best fit. So pause the video and graph the ordered pairs and draw your line of best fit. So your graph should look something like this, where you have mine are green dots and then that blue curve of best fit. Here we are on to page 248, and here we have another situation where we have seconds and grams in our table. All right, this table shows the number of grams of radiation after X seconds. So we're going to follow steps 1, 2, and 3 on our Desmos.com calculator to determine if the relationship is linear or exponential, and to find the equation of the line or curve. And so let's go ahead and flip over to our Desmos.com calculator. Okay, so back here with all the work we've already done, I'm going to go ahead and just hit X here on the 2. I'm going to come up and hit X on that first as well. And that way we can have a clear slate. So we're going to go plus to the table, and we're going to enter in the information from this table about radiation after the number of seconds. So remember, seconds is going to be our X value. Grams of radiation will be the Y value. So I'm going to start putting it in. I'm just going to go 1, 2, 3, going down the X values. And I noticed that they're not skipping any all the way up to 20. So I'm just going to keep going 4, 5, 6. You can see now it's found my pattern. I can just keep hitting enter all the way down to 20. I go over and I come back up to the top and put in my Y values. So go ahead, pause the video and finish entering the information into your table. And then we'll set up our window and find our line of best fit. So go ahead and pause the video. Okay, so now that I got all the information here in my table, I'm going to go ahead and go over to this wrench, and we're going to set up our scale. Well, not the scale, but the actual numbers, our X min and max. So the X min, we're going to go a little less than 0. So let's go 1, or sorry, a little less than 1, which is 0. Switch those for a second. And then we're going up to 21. So let's just go to 20. So we're going to put in 21. Getting ahead of myself. Okay. Now for the y-axis, our smallest value is 17.7, but maybe we should look at it from 0, and we'll go all the way up to 40, just a little bit above that 39.8, so we can still see that point. And you can see here what that curve is doing. Now, if we went back up to the wrench and we switched this out and said, let's just go a little bit less, so let's do like 15, now you can see it even more. We got this really nice curve going on, and a line through this wouldn't work. I could put a line pretty close to these points, but most are going to be right above or below, and then we got this one off here. So we have to take that one into consideration, which helps us say, yeah, this is definitely going to be a curve. If we want to double check, what we could do is we could go ahead and type in here. We could go Y1, and then remember the similarity is a shift and right above the tab. And then we could go MX1 and then plus B. Now looking at this, you'll notice that our R value is negative 0.8938. That's the correlation coefficient. Now, if we go back and we say, okay, I'm going to switch this up. I'm going to switch it over to an exponential and say A times B. Then we got to use the caret, which is shift 6. And then we go X1. And we put in the log mode here. And we go back now and we say, hey, this has a better correlation coefficient. This is a 0.941, negative 0.941, which is better. It's a stronger correlation. So we're going to use this exponential as our curve of best fit equation. Okay, so using that Desmos.com calculator, we now have this information, and I've put it right here from the Desmos.com calculator to write the equation for the curve of best fit. Now we're going to round A to the nearest whole number and B to the nearest thousandth again. And so we're going to start out here with Y equals, and then we're going to go to A. A is 32.6451. Now, we're going to round to the nearest whole, so that 6 tells us to round up, and that's going to be 33. Then our B value, 0.967491, nearest thousandth, so it's 3 decimal places. The 4 tells us to keep it the same, so it's just going to be 0.967. And we're going to raise it to the xth power. And there's the equation for this curve of best fit. Now, what's the R coefficient? We're going to round this to the nearest hundredths. That's 2 decimal places. So this 1 tells us to keep it the same. It's negative 0.94. And that's our R coefficient, or correlation coefficient. Then, number 17, what is the correlation? So based on this, we're kind of in that high range, that 0.94, and close to -1 or 1. Here we're close to -1, so it's still strong. But because the value is negative, it's a strong negative correlation. Number 18. We're going to write a sentence explaining the initial value, A, and what it represents. So remember, we're talking about time would be 0, and this is a point. It's going to be a point where we have the x value of 0 and the y value of 33. Okay, that's what's in our equation. And so we're going to say that at 0 seconds, so there's the x value, we're going to say that there are 33 grams of radiation. And that is our initial value. Number 19. We're going to write a sentence explaining what the decay factor, B, represents. So just like before, we want to go back to that percentage, right? And so there's a couple different ways that we can approach this, as we've discussed in previous units this year, okay? But here our decay factor is 0.967. So we could word this two different ways. And the way I'm going to word it is I'm going to say that every second, because this is what's happening over each second, okay, there is 96.7% of grams of radiation left. Okay, so these last two, numbers 20 and 23, we're going to try to decide if these are linear or exponential. And then we're going to give a little bit more information about them. Now, one thing we could do is we could just take this information, type it into our Desmos calculator and check and see, hey, is this linear or exponential? But something that can be an easy, just quick check, so you don't have to go through that process, is to look and say, okay, what's the change look like? This is 3, this is, what is that? Let's see, 7. Right here we have another 7. Here we have 22, right? Here again, we're looking at 5. I mean, not super consistent. But then this one is about 30. And so it looks like it's growing faster, but I'm not sure. Let's check the x's. So this was a 3, this was 2, this is 4. And so those are pretty consistent here. 10 to 15 is 5. That's kind of interesting that one's that much bigger. This is 1. This is 6. And so looking at those, maybe that's close. 30 divided by 6 is 5. 1 divided by 5, or 5 divided by 1 is 5. 22 divided by 5 is 4. 7 divided by 4. Now that's a little bit weird that that's so small. There's a couple 1s and 2s. But to be sure, we could switch over to our Desmos.com calculator and double check just real quick by typing it in our table again and graphing it. So let's go ahead and do that real quick to just double check. But right now I'm probably leaning towards linear because there's not a huge change in what's happening here in our table. Okay, so here we are again. I'm just going to hit X. I'm going to exit out of these, and we're going to take a look at our new information. So I'm going to add a table, and I'm just going to quickly type it in. We got 1, then we have 4, 6, okay, and so on. So go ahead and type in the information from our table in number 20 in this table, and then hit play. So go ahead and pause the video and enter the information in the table. Okay, now that we have the information in the table, we're going to go over to our wrench here. We're going to go and set up our parameters. So we're going to go from 0 to, let's say, 25 maybe, just to get everything in on the x's. And then the y's, we can go from about 0 to 80. That way we see everything in our graph. You can see it here. Maybe a slight curve. I'm not sure. We'll take a look. I'm going to zoom out just a hair. Oh, zoomed out too much. But you can kind of see what's going on there. Next, what I'm going to do is I'm going to type in and check the correlation coefficient. So I'm going to go Y1, then I'm going to go shift and right above the tab for that similarity sign. And then I'm going to go MX1 plus B. And I'm looking at this, my correlation coefficient over here where R is 0.9786. So we're going to remember that, 0.9786. Now I'm going to go back and I'm going to switch this to a exponential and see what that does to my correlation coefficient. So here we got it as a 0.9748. So I think the linear is going to be a better fit for what we have. So I'm just going to flip back real quick to that linear. This is 0.9, okay, 748 for exponential. And if we go back to our linear, we'll notice that this one is going to be a better fit for us because it's 0.9786, just slightly better, but it's telling us, hey, this is a better linear situation than it is exponential. And so when we go back to our number 20 on our notes in 21, what we're going to do is we're going to go ahead and write out this equation using this information. So our slope rounded to the nearest whole number would be 4, and our y-intercept rounded to the nearest whole number would be a -8. So let's go ahead and flip back to our notes and write that equation for number 21. Okay, so on number 20, we're going to write our equation on 21. So it's going to be y equals 4x's minus 8 because we rounded them to the nearest whole. Now, using this equation, we're going to predict the y value if the x value is 50. So what that means is we're going to substitute 50 in for x in our equation and solve for y. So we're going to have y is equal to 4 times 50 minus 8. Well, 4 times 50 is 200. If we subtract 8 from that, we're going to get the value of y, which is 192. Okay, so number 23, we have our x and y values. And notice here, if we follow the same pattern we did with 20 and just look at the change, this is a change of 15. Here we got a change of 30. Here we got a change of like 420. And it's growing a lot each time. And you can see those numbers under the y's changing quite a bit. Well, on the other side, it's 2, 2, 4, 3, 4. You know, not a lot of change here, 3s and 4s and 2s, but that change in y is so drastic that this is definitely going to be an exponential. We can see that just from the table. So we're going to write the equation for our line or curve of best fit. Okay, for number 23, it's going to be a curve of best fit, right? And we're going to round our numbers to the nearest whole numbers. So again, we can flip back to that Desmos.com calculator, enter this information, and then we're going to figure out that curve. We don't have to look at the graph in this case, but if we have time, we will. Okay, so I've already cleared everything out of my Desmos.com calculator page by hitting these X's. I pulled up another table by hitting plus and table. Now we're just going to type in the information, 1, right? Then we got 5. Go ahead and type in all the information in the table. Okay, and then you're going to write in your equation for an exponential in number 2. So pause the video, do that, and hit play when you're done. So here it is. You can kind of see that graph. I'm going to zoom out just to kind of help us visually see what's going on here. You see that quite a curve here, okay, especially towards the end there. And then I typed in our equation over here for this curve, since we decided it was exponential. And you can tell by this correlation coefficient, the 0.9997, that is so strong, okay, that it's really saying there's probably no way this is linear, okay? And so we're going to take that information and we're going to use the a and b rounded to the nearest whole to write our equation in our notes. Okay, so rounding to the nearest whole, we're going to have y equals, and then our a value rounded to the nearest whole is going to be 3, times our b value, which is going to be rounded to the nearest whole, 2, raised to the xth power. And then on number 25, we're just going to substitute in for the x value of 25 and find y. And so we're going to have y equals 3 times 2 to the 25th power. Now, since this is such a big number with an exponent, we're going to probably want to use our calculators. So typing it in, we go 3 times 2 to the 25th power. And if we do that, we would get that y is equal to 100,663,296. That concludes this video of Lesson 5-3 for Secondary 1 Math, Scatter Plots.